Okay, so greetings there, everyone. In this video, we will be dealing with special functions. Especially, we will be dealing with the Legendre's function in general. All right. So in this video, we'll be dealing with Legendre's functions. So first of all, we will deal with the Legendre's differential equation and the solution of the Legendre's differential equations in general known as the Legendre's function. So let's write the Legendre's differential equations first. So the form of a Legendre differential equation is just like 1 minus x square times d square y by dx square minus 2x into dy by dx plus n into n plus 1 y equal to 0. Okay, and the solution of this differential equation is given as that its solution. Its solutions are, okay, we can write y equal to a times Pn of x plus b times Qn of x. So this Pn of x and Qn of x are generally known as the Legendre's function. So in general, these Legendre's functions appear, or these Legendre's polynomials appear in many different mathematical and physical situations. And so these functions or these solutions are generally arise as the solution of the Legendre's ordinary differential equation. Okay, so it's a second order differential equation and its form is given as follow. Okay, literally on the examination point of view, we don't need to by heart all these kinds of things, but we just need to know a general understanding of it. And if it is possible, just try to by heart it. Sometimes even I forgot these equations while we deal with a lot of things, or we revise it on the previous day of the exam. Usually I forgot these kinds of things. I just try to skip to remembering the sessions. Okay, so the solutions of this differential equation, so especially the Pn of x is given as Pn of x equal to 1 into 3 into 5 into etc. up to the odd powers 2n minus 1 divided by n factorial times x raised to n minus n into n minus 1 divided by 2 into n minus 1 raised to n minus 2, etc. So these are the solution, and in order to get the Pn of x or the Legendre's polynomial, we have a Rodrigues formula, the Rodrigues formula, the Rodrigues formula. So you have to by heart this Rodrigues formula. Pn of x equal to 1 by 2 raised to n factorial n dn divided by dx raised to n of x square minus 1 whole raised to n. So this is really important. So you have to write it down and you have to by heart this Rodrigues formula. Really important. So I hope in some text it is given as factorial n. Literally, this representation mean n factorial or the factorial n. So let's try to find out the first few Legendre's polynomial. If n equals 0, but we will get p naught of x or p0 of x. So we are just going to substitute in this equation. We will get 1 upon 2 to the power 0 divided by factorial 0, d raised to 0 divided by dx raised to 0 into x square minus 1 raised to 0. So all these things becomes 1. So we got p naught of x as 1. Okay, p naught of x is 1. Let's do the next thing. So if n equal to 1, we got p naught of x equal to 1. Okay, so I'm just going to write it over here. P naught of x equal to 1. Okay, let's do the next thing. We have to find p1 of x. P1 of x, which is equals 1 upon 2 to the power 1 factorial 1 d by dx x square minus 1 upon 1. Okay, so we have to differentiate this. So this becomes 1 upon 2 to the power 1 is 2 and factorial 1 is 1. And on differentiating, we will get this is 2x and this becomes 0. So we got x, that is p1 of x equal to x. All right. So similarly, so we can find other terms, p2 of x, p3 of x, and p4 of x, etc. Suppose if we are trying to plot p of x against x, so here we will be having n of x against x. I'm just going to plot the first one, the first figure, which is, yeah, I will do in the next slide. So let this be p naught of x and let this be x. So we got p naught of x equal to 1. For all x, we got p naught of x equal to 1. So this is the figure for p naught of x. All right. And for the second one, we got p1 of x. p1 of x against x. So we got the function is equal to x. So we have already learned the function will be like, okay. And just try to by heart the first few Legendre's polynomial. That will be better. Like I will write here. Let p2 of x equal to 1 by 2 times 3x square minus 1. Right, so I will just write these things in order, okay? So don't just try to listen to the lecture, just try to write it down if it is possible. Like time is really important factor while we're dealing with these kinds of competitive exams. Literally, most of the people, even me is wasting time just scrolling Instagram videos, YouTube videos, and watching some stupid films. So I literally don't suggest you to go in that way, especially in the examination period. Just try to write these things down. Okay, so I'm just going to write that again and to try to by heart this. P naught of x equal to 1 and p1 of x equal to x and p2 of x equal to 1 by 2 times 3x square minus 1. Okay, let's just try to draw the figure of p2 of x. It is 1 by 2 times 3x square minus 1, right? Okay, let's just try to draw. So this is p2 of x, that is 1 by 2 times. Suppose if x equal to 0, p2 of x becomes minus 1 by 2, right? So it will be over here minus 1 by 2, and this is just similar to a parabola, right? So we will get a equation similar to a parabola. So this is similar to a parabola. Okay, and it will be better like if we try to remember this function in terms of the figure or the graph. It will be much more easier for the calculations. Okay, and p2 of x we got this, and p3 of x, this will be become 1 by 2 times 5x cubed minus 3x. p4 of x equal to 1 by 8 times 35x to the power 4 minus 30x square minus 3, and p5 of x equals 1 by 8 times 63x raised to 5 minus 70 x to the power 3 plus 15x, and so on. So literally we can find all these things from the Rodriguez formula. Okay, we can find all these things from the Rodriguez formula. If you substitute p if we substitute n equal to 1, we will get p1 of x. If we substitute n equal to 0, we will get p naught of x. And similarly for n equal to 2, n equal to 3, and n equal to 4, and n equal to 5, we can find all these kinds of things. And so we can get an idea from here. Suppose if n is even, so this here we are just considering this 0 as even, or just we can start from 2, 4, and so on. 0, 2, 4, and so on. For even n series, so these things terminate with what? Terminate with an integer. So let's see. So this terminates with an integer, right? Yeah. And p2 of x, this also terminates with an integer. And p4 of x, this also terminates with an integer, right? Okay. And how about the odd ones? How about the odd ones? It terminates with what? X. p1 of x. This is odd one. This is odd n. Here 1 and here 3, and also we have for 5. So these things terminate with what? X. And p3 of x, so here also terminate with x, and it's also terminate with x. So we can say for even n, pn of x is even, and for odd n, pn of x is an odd function, right? So for even n, pn of x is even and terminates with 1 or an integer, and for odd n, it terminates with x, so p n of x will be an odd function. Okay, just let's write these things down. Okay, even n series terminates with integers. So this corresponds to what? So, and Pn of x will be an even function. All right. And similarly for odd n series terminates with x corresponding to Pn of x would be an odd function. Okay, so these are the general things that we need to understand about the Legendre's functions, which are the solution of the Legendre's differential equation. And most importantly, we have to by heart the Rodrigues formula and the first few Legendre's series, the Pn of x, like P naught of x, P1 of x, P2 of x, 3, 4, 5, and 6. So sometimes we might forget. So I suggest you to learn these kinds of things far more before the exam and just try to revise these things a lot often. Okay. And Rodrigues formula is really important, and the form of the Legendre's differential equation. And we will be trying to learn the most important thing in the Legendre's differential equations, not just for the Legendre's differential equation. This is applicable for Laguerre's differential equation, Hermite's differential equation, and Bessel's differential equation and their solutions also. So here for Legendre's differential equation, so we have a generating function, the generating function. The generating functions of the Legendre's differential equation is given as sum over n equals 0 to infinity h to the power n Pn of x. So this is the form of the Legendre's differential, sorry, the Legendre's function, and it is given as 1 minus 2xh plus h square to the power minus 1 by 2. So this is in general what? This is in general 1 by root of 1 minus 2x plus h square. All right. Okay. So we have to by heart this generating function, or sometimes it would be given in the question itself, but I suggest you to write it down and try to by heart this generating function. Okay, so let's see. So I'm just going to put x equal to 1. Okay, just try to put x equal to 1. So we will get sum over n equals 0 to infinity h to the power n Pn of what? Pn of 1. Pn of 1, which is equals 1 minus this becomes 2 into 1 into h. 2h plus h square to the power minus 1 by 2. Okay. So this we can write as a minus b the whole square, right? So this will be in the form of 1 minus h the whole square raised to minus 1 by 2, which is equals 1 minus h. These two cancels each other, raised to minus 1. So if we are doing the series expansion, we will get 1 plus h square plus h cube plus etc. So this is the form when we substitute x equal to 1. Okay, similarly, I'm just going to expand this term also. Okay, so let's see what we will get. So this we will get if n equals 0, if n equals 0, h raised to 0, which is 1. This is also 1. We will get 1 plus, when h equals to 1, 1 plus h times p1 of 1 plus h square plus p2 of 1 plus h cube p3 of 1 plus etc. Okay, so here the coefficient of h to the power n h raised to n is the Legendre's polynomial of order n. Okay, so we got p n of 1, that is p n of 1 equal to 1. So that is our first property. We got p n of 1 equals 1. This is our first property. That means if p naught of 1 equal to 1, p1 of 1 equal to 1, and p10 of 1 is also equal to 1. So these are our this is our first property. So similarly, that means p1 of 1 equals p2 of 1 equals p3 of 1 equals etc. So we got pn of 1 equals what? 1. So this is an important property that we just need to learn for this is for x equal to 1. Okay, so let's do one more property for x equal to minus 1. For x equal to minus 1. So what was our generating function? Just try to by heart the generating function. It is h to the power n pn of x. H to the power n pn of x, where n equals 0 to infinity, which is equals 1 minus 2xh plus h square to the power minus 1 by 2. Okay, so right now we are just going to substitute x equal to minus 1. So let's see how this function behave. Okay, so similarly, if I put x equal to minus 1, this becomes 1 plus 2h plus h square to the power minus 1 by 2. Or so this is in the form of a plus b the whole square. This becomes 1 plus h the whole square to the power minus 1 by 2. These things cancels each other, and we will get 1 plus h to the power minus 1. So if we do a series expansion, we will get, I'm just going to write, yeah, I will write over here. So we will get 1 minus h plus h square minus h cube plus h raised to 4, etc. Okay, right? So if I substitute here in this, so I will get 1 plus h of p1 of minus 1 plus h square p2 of minus 1 and so on. So the coefficient of h raised to n represents the nth order of the Legendre's function. Okay, let's see. So here the coefficient of h, that is p1 of minus 1, p1 of minus 1, the coefficient of h is what? Minus 1. The coefficient of h is minus 1. Okay, so similarly, just we can write the coefficient of h raised to n's are, so we have p1 of minus 1 equal to what? Minus 1. Okay, let's see. And p2 of minus 1, this is p2 of minus 1, and here it is plus 1. Here it is plus 1. Okay, p2 of minus 1 is plus 1. And if we look at the odd powers, we will get minus 1, and for even powers, we will get plus 1. So in general, we got a second property, pn of minus 1 equal to minus 1 to the power n. So we have to by heart this. Okay, or in general, we can write Pn of x equals minus 1 to the power n of Pn of x. Okay, so these things are the properties of the Legendre's functions. So we have to by heart these properties. So in so these things are not confusing, but since we are not familiar with these kinds of things, we might forget these kinds of things. So I suggest you to revise these things very often and just try to do a lot of problems, previous year PYQs. And so in this lecture series I will be also doing the PYQs. Okay, so let's do some properties. So P1 of 1. So we know P1 of 1 is what? 1. P1 of 1 is 1 and Pn of 1 is 1 and Pn of minus 1 is minus 1 to the power n. So for here for x equal to 1 and here for x equal to minus 1. Okay, so what were the properties of these functions? For even n, so which are the even n? For 0, 2, 4, 6, and so on. For even n, Pn of 1 was 1. And for odd n also, for odd n, which are the odd n, 1, 3, 5, and so on. For odd n, Pn of 1 is 1. But here, for even n, for 0, 2, 4, 6, and so on, Pn of 1 is, Pn of minus 1 is 1. And for odd n, this is 1, 3, 5, and so on. Pn of minus 1 equal to minus 1. So far we came across these things and we have to remember these things. Okay, so I already told you. So first of all, we have to remember the Legendre's differential equation, the form of the Legendre's differential equation, and also the Legendre's polynomial function and the Rodriguez formula in order to get the P naught of x, P1 of x, P2 of x, P3 of x, P4, 5, 6, 7, and so on. And just try to remember the first few series of the Legendre's function. It will be much more beneficial. And the next thing is the generating function. We have to remember the form of the generating function. And sometimes in the question itself, it will be given. And suppose if it is not given, so we have to remember a way to get the Pn of x, and substituting the value of x, we will get a different terms. So initially we have done for x equal to 1 and we got the coefficient of the uh, power of h, that is h raised to n. The coefficient of h raised to n gives the nth order polynomial, Legendre's polynomial. And for x equal to minus 1, we also got different kinds of functions for even n and also for odd n. For x equal to 1, it doesn't matter whether the n is even or odd. And for x equal to minus 1, so we have to think about the form of the function, whether it is minus 1 or plus 1. And the next thing we are going to learn is the orthogonality property. Orthogonal. orthogonality property. Orthogonality properties. So since here we dealt with the x from -1 to +1, so in general this orthogonality property is also from x to -1 to +1 Pn of x times Pm of x dx equals 2 upon 2n plus 1 Kronecker delta mn. And we have to by heart this property. So integral over the limit -1 to +1 Pn of x times Pm of x dx is equal to 2 upon 2n plus 1 Kronecker delta mn. This is an important property that we have to learn. So literally all you guys know about the form of the Kronecker delta mn, right? Kronecker delta mn equal to 1 if m equal to n and 0 if m not equal to n. That means this is only valid when the Pn of x and Pm of x are the same, like not the same, like the n should be equal to m. The n should be equal to m. So this is the orthogonality property. Just try to write it down and try to by heart the orthogonality property. Okay. So here we have two conditions. So if n equals m, we get integral -1 to +1 Pn of x the whole square dx equal to 2 divided by 2n plus 1. So else, so here the condition is if m equals n, and suppose if m is not equal to n, if m is not equal to n, we will get integral -1 to +1. I will just write it over here. Integral -1 to +1 Pn of x times Pm of x dx will be equal to 0. This is an important property that we have to learn in the Legendre's differential equation. So just try to remember the form of the orthogonality property, that is integral -1 to +1 Pn of x times Pm of x dx is equal to 2 upon 2n plus 1 into Kronecker delta mn. Kronecker delta mn. Okay. So let's do a few problems. Let this be, I'm just going to give you a question. Just try to solve -1 to +1 P1 of x times P3 of x dx. So literally we just need to, so what will be the answer? I'll give you a few seconds to do. So here m is not equal to n. So the answer is 0. Okay. Let's do a second property. Integral -1 to +1 P3 of x times P3 of x dx. So what would be the answer? So this is in form of integral -1 to +1 P3 of x the whole square dx, right? So here m is equal to n, so the form will be 2 upon 2n plus 1. 2 upon 2n plus 1, which is equal to 2 upon 2 times 3 plus 1, that is 2 upon 7. This is the answer. Okay, so I will give you one more question to do. So integral -1 to +1 p11 of x times p11 of x dx. Just try to solve. So what would be the answer? Here m is equal to n, right? Here m is equal to n. So we will get 2 divided by 2n plus 1, which is equal to 2 divided by 2 times 11 plus 1, equal to 2 divided by 22 plus 1, 23. So this is the answer. Okay, I hope you're getting it, right? So next we will deal with the recurrence relations. Next, we will deal with the recurrence relation, and in the next session, we will deal with the some more special function. I will give you a hint and an idea to remember all the recurrence relation with certain kinds of codes. Just write down. Just try to write down the recurrence relations. So from the recurrence relation, we can find Legendre's differential equation, and the first two recurrence relation, n times Pn, n times Pn equal to 2n minus 1 times x into Pn minus 1 minus n minus 1 times p n minus 2. So these, so this is Legendre's function of nth order, and this is Legendre's function of n minus 1th order, and this is Legendre's function of n minus 2th order. Okay, and so this, the next one is p n times pn equals x times. So here we are going to do the derivative, the first derivative minus p n minus 1 first derivative. So this is the first two recurrence relation, and we have to by heart these first two recurrence relation, and the next two recurrence relation are given by 2n plus 1 times Pn equals Pn plus 1 minus Pn minus 1 prime, and n plus 1 Pn equals Pn plus 1 prime minus x into Pn prime. So these are the next two recurrence relations. Okay, I hope you have written, and we can deal with the next two recurrence relation. 1 minus x square times p n prime equals n into Pn minus 1 minus x into Pn, and 1 minus x square Pn prime equals n plus 1 times x into Pn minus Pn plus 1. So these are the next two recurrence relation, and we have to remember the form of the recurrence relation. So from this recurrence relation, we can get the next two or three terms of the Legendre's functions or the series. Okay, so let's do a PYQ. So this question was asked in CSIR JRF December 2011. Okay, the question is like this. The generating function, the generating function f of xt equals sum over n equals 0 to infinity pn of x t to the power n for the Legendre's polynomial pn of x, and it was given that f of x, f of x t is 1 minus 2x 2xt plus t square to the power minus 1 by 2, right? So we already dealt with the form of the generating function. The value of the value of p3 of minus 1 is, so options were also given. The options were like this: option A 5 by 2, option B 3 by 2, option C 1, and option D minus 1. Okay, so we can approach this question in two different ways. So we have already learned the form of pf minus 1, right? So we can approach this in two different ways. So we know Pn of minus 1 is minus 1 to the power n. Here it is asked to find P3 of minus 1, right? P3 of minus 1, P3 of minus 1, which will be minus 1 to the power 3, which is equal to minus 1. So literally, we got the answer. We don't need to do a big calculations for this. So we got the answer is option D. Okay. Suppose we are interested in finding the solution by the series expansion, right? And we have already learned the form of p3 of x. So what was the form of, this is the first method, right? First method. And a second method. So I already told you to remember the first few forms. What was p3 of x? P3 of x is equal to 1 by 2 times 5x cubed minus 3x. So P3 of minus 1. P3 of minus 1 will be 1 by 2 times 5 to the power minus 1 to the minus 3 into minus 1, which is equal to 1 by 2 times minus 5 plus 3, which is equal to minus 2 by 2 equal to minus 1. Okay, so we got the answer. It is minus 1. So we have already dealt with how we can find the form of the nth order of the Legendre's functions. Okay, so suppose the question was like, I'm just trying to rewrite the question. So suppose if it was asked to find P3 of 1, what would be the answer? Suppose if the question was like to find P3 of 1. So we already learned, right? So what was Pn of 1 is always 1. Pn of 1 is always 1. Suppose if it is P1 of 1, or if it is P2 of 1, or even if it is P3 of 1, it's always 1. Or we can also, this is the first method. And we can do the same thing by remembering the form. So what was our P3 of x? P3 of x is a 1 by 2 times 5x cube minus 3x. So I already told you, if n is even, if n is even, the polynomial terminates in an integer. Here n is odd, the polynomial terminates in what? In x. So P3 of x, this is our second method. Therefore, substituting P3 of 1, just let's do 5 times 1 to the power 3, that is 5 minus 3 into 1, 3, which is equal to 2 by 2 equal to 1. Okay, so we can find the form of the Legendre's function by remembering the first few terms. I suggest you to learn up to 8 terms. That will be better, and also just try to derive the formula up to the first few terms. Okay, so for the revision, I will give you a few hints. Okay, let's do a question. Integral -1 to +1. P1 of 1 times P2 of 1 dx equal to what? Okay, let's try to do P1 of 1 times P2 of 1 equal to dash. Okay, so how we will do using the orthogonality property? Literally, we don't need to go do with the orthogonality property over here, right? So we know P1 of 1 is 1 and P2 of 1 is 1. So this becomes what? The answer is integral -1 to +1 dx, which is equal to x with lower limit -1, upper limit +1, upper limit +1 minus lower limit -1, that is equal to 2. So the answer is 2, right? Okay, I hope you get it. Suppose if the question was like this, integral -1 to +1, P1 of x times P2 of x dx equal to. So what would be the answer? Here, m is not equal to n, right? So answer is 0. Next question. Integral -1 to +1. P2 of x times P2 of x dx. What would be the answer? P2 of x times P2 of x. So this is integral -1 to +1 P2 of x, the whole square, right? Here m is equal to n. So the solution will be 2 upon 2n plus 1. That is 2 into 2 plus 1. 2 by 5. Right. So let's do one more property. So I'm just giving you prove that sum over Pn of x equal to 1 by root of 2 minus 2x. Also, we can also change the question like this. Okay, so yeah, I have already asked you to prove this, right? Prove that. So in the CSIR point of view, the question can be asked like this. Let Pn of x be Legendre's polynomial of order n, and given by a generating function. The generating function can be given, or sometimes they won't provide the form of the generating function, so we have to by heart it. And what would be the form of sum over n Pn of x? So this is the question, and few options will be given like A, B, C, and D. From this A, B, C, and D, we have to find out the actual form of the sum over n to infinity, Pn of x. So we are going to find the solution, right? So we have the generating function is in the form of n equals 0 to infinity h to the power n Pn of x